So the pressure of gases also has a big influence on our weather. The Earth's atmosphere has a pressure. That pressure can vary. Now, in terms of us breathing in and out, the pressure around us is going to be constant. But overall, the pressure can be higher or lower. And this is what the weatherman's talking about when he talks about this low pressure front and the high pressure front and how this is moving in, etc. Low pressure is usually associated with unstable weather, high pressure with clear weather. And so like we've got this barometer in here, and it's telling me that the pressure right now is 29.85. So that's a little bit lower than normal, and so that's associated with clear weather, and it's a clear day out there. This also has little pictures on it that kind of predict what's going to happen next, and that's based on whether the pressure is rising or falling. The number of gas particles in a given volume of air is going to decrease at higher altitudes. So the higher up you go, like if you drive up to Grant Grove, the air, we say, is thinner, right? And you tend to get out of breath more easily because there's just not as much oxygen in the air. There's not as much nitrogen. There's actually not as much air in the air up there. So the pressure is lower. So as you go higher in altitude, the pressure decreases. So the pressure we've been talking about is dependent on how many particles are in a given volume. So here we've got two mason jars. This one has fewer particles, that one has more particles. And if you think about these little particles, they're just moving in a straight line until they bump into something. There's a lot more particles here, and so they're going to exert more of a pressure on the walls of a container. Sometimes I think of gas particles as being a little bit like kindergarten children. So if you have, fewer kindergarten children in the same size room, there's going to be less collisions, right? Kindergartners just kind of run around willy-nilly. And over here, with more children in the room, there's going to be more bumping into each other. There's more collisions. Does that make sense? So higher pressure with more particles. So the pressure then is related to the density. So we've talked about density before. What's density? Mass over volume. So these two containers have the same volume, right? Which container has a higher higher mass of gas? The one with the higher pressure. The one that has more particles, right? So higher gas density corresponds to higher pressure. So pressure imbalances affect your ears as well. If you've ever been to the mountains or ridden in an airplane, you know that your ears pop, right? So what happens is you've got an eardrum that separates your inner ear from your middle and outer ear, and there's space on the inside. Your inner ear is connected through your eustachian tube into your throat, and there's a pressure, there's gas in here and there's gas outside. So if you drive up the hill to Grant Grove and the external pressure decreases, the internal pressure inside your ear remains the same until your ears pop. That increased pressure on the inside compared to the outside causes your eardrum to bulge out. And if you've got a bad cold or something, that can be extremely uncomfortable. But your ears pop, and then the pressure difference is resolved, and everything's good again. When you're coming back down, then the pressure outside becomes greater than the pressure inside. Your eardrum's going to bulge the other way. And again, you need to get your ears to pop. And that popping sensation is the air flowing in or out of your eustachian tube. Any questions about that? Ear pain is usually why small children scream on airplanes. So if that gives you any more sympathy for them. They're in pain. Their ears hurt. Of course, some of them just scream because they're ornery, and you can't tell the difference. How do we measure pressure? Well, this is the original pressure measurement device. a Mercury Barometer. This was invented or discovered by a man named Torricelli. So this consists of a long glass tube, kind of like a really big test tube, filled with mercury and then inverted into a dish of mercury. Mercury is pretty cool stuff because it's a liquid at room temperature, but it's a metal and it has a very high density. Unfortunately, it's also toxic, so then we don't get to play with it, but it's really neat stuff. So what happens is you turn this test tube over, and some of the mercury will come out, leaving a vacuum up here. But it won't all run out. And what we've got here is opposing forces. We've got atmospheric pressure pushing down on the surface of this dish of mercury, which is supporting the column, and then we have gravity pulling the mercury down. And so the mercury will come down in the tube until those forces balance each other. And regardless of the size of the tube, the diameter, Torricelli found that the height of the column of mercury was pretty constant. It's about 760 millimeters. And so that is a pressure unit that seems kind of weird. How does a length of an element constitute pressure? But it's the height of a mercury column. So at normal atmospheric pressure, which is defined as sea level pressure, the height of a column of mercury will be 760 millimeters of mercury. That was given the fancier sounding name Tor after Torricelli, and I think the hope was that this unit would replace millimeters of mercury. But in fact, what has happened is we use both of them. So that's kind of unfortunate and confusing for students. A torr and a millimeter of mercury are exactly the same size pressure unit. They're just different names for the same thing. So this is 760 millimeters of mercury. We can also say it's 760 torr. So what Torricelli noticed is if he took this contraption and walked up in elevation, that the height of the column of mercury got lower and lower as he walked up because the atmospheric pressure is lower at higher altitude. And then if he walked this back down the mountain, the height of the column of mercury went up again because the increased atmospheric pressure can support a taller column of mercury. And this is extremely low tech. There's, some glassware, some mercury involved, and then you need a ruler to measure the height. In inches, that would be 29.92 inches. And that's the unit that the meteorologists use. So the barometer here is saying 29.85. That's inches of mercury, which is slightly less than normal atmospheric pressure. Any questions? There are lots of different pressure units. We have different units because they're useful in different situations. So some of these we'll use a lot and some of them not at all. The ones that are important for us are atmospheres. It's abbreviated ATM. It's not a thing you get money out of. The torr and the millimeter of mercury are exactly the same thing. Now the way this table is set up is all of these are equal to each other. These all represent the average air pressure at sea level. So 1 atmosphere is normal average air pressure at sea level. 760 torr, that is an exact relationship. 760 torr is exactly 1 atmosphere. So that relationship is one I'm going to expect you to know. 1 atmosphere, 760 torr, 760 millimeters of mercury. The rest of these you may need occasionally. If they're on an exam, I'll give them to you. So 1 atmosphere is also 29.92 inches of mercury. You're going to need that conversion for lab today. You can convert it through all kinds of steps, but the pressure units you can always do in just one step because all of these are equal to each other. Pascal is the official SI unit. So a pascal is 101,325 pascals is 1 atmosphere pressure. So that's a very tiny unit. One you might be more familiar with is pounds per square inch, PSI. That's what you'd use to measure the pressure in your tires. So 14.7 is normal atmospheric pressure. So if your car tire, say, is 55 psi. That's in addition to the atmospheric pressure. Yeah. So let's practice converting. And this is the sort of information that I would give you on an exam. So these are all equal to each other. I might, depending on my mood, I might leave this one off because you should know that an atmosphere is 760 torr. Okay, so the local weather report announces the barometric pressure 30.44 inches of mercury, and that looks like in mercury, that's inches of mercury. Convert this pressure to psi. So dimensional analysis, we can do this in one step. So we've got 30.44 inches of mercury, and we need one conversion factor. We're going to psi, so we put that on the top. We put the unit we're starting with on the bottom. Then we go to the pressure table. And we see that 14.7 psi is equal to 29.92 inches of mercury. We do not have to go through atmospheres. These two things are equal to each other. We could also do pascals to inches or pascals to torr, any combination. So I just find the number in front of psi in the pressure table, 14.7, and the number in front of inches of mercury is 29.92. So 30.44 times 14.7 divided by 29.92. And I get 14.955. According to this would only have three significant figures. So that would be 14.9, and then we'd round up, so we would express this as 15.0 psi. Any questions? So the barometer is used to measure atmospheric pressure. How do you measure pressure in a container? Well, there's lots of fancy ways to do that now, but the original method was called a manometer. So a manometer is a U-shaped tube containing mercury, and you attach one end of the tube to the sample of gas whose pressure you're trying to measure, and the other end of the tube is open to the atmospheric pressure. If atmospheric pressure and the pressure of the gas are equal, then the mercury will go to the lowest part, and the height of mercury in each side will be equal, right? You can imagine what would happen if you disconnect this. If you've just got a U-shaped tube, think of what would happen if you had water in there. It would go to the bottom, and it would be equal on both sides, right? So why is the mercury lower here? Because there's higher pressure. Imagine blowing into the straw. You can move the water down on this side, and it has to go up on the other side. So the higher pressure here is causing the mercury to go down here and get pushed up there. So we can measure the pressure of this gas relative to the atmosphere. And again, you would use a ruler and just measure the height difference between the one arm and the other arm. So this difference H is the difference in pressure between this gas and the atmosphere. Does that make sense?